Hello and welcome to the latest video on circular motion from me, Mr. McIver, here at the London Central and Northwest Maths Hub. Once again, I'd like to thank Dr. Michael Gallus of Penn State University for his animated simulation of a car looping the loop. Quick reminder of what I expect you to know. You need to know about angular speed, the units in which it's measured, and some of the basic equations relating to constant angular speed. We're going to be talking a lot about energy today, so you need to know about GPE, gravitational potential energy, and kinetic energy. Today we are focusing on vertical circular motion, in particular when it goes wrong, when the forces no longer balance and circular motion breaks down. And we're going to start by looking at an example of a car trying and failing to loop the loop. Here's our car heading at 10 meters per second towards that dangerous looking vertical loop. I want you to pay close attention to the yellow bar at the top right of the screen. This is actually a measure of the normal reaction. You see what happened there? The normal reaction between the track and the vehicle has fallen to zero. That is the instant at which the car starts to part company from the track. It looks like it's round about 1 o'clock on a clock face if you think of the loop as a clock. But let's see if we can be a little bit more precise with that position. So here's the car at the point where we think it left the track. I'm going to start by drawing in a vertical radius, and now I'm going to draw in a normal line from the circle to the center. We'll call the angle between those two lines theta. This is how we are going to define the position of a point on a circle. Now that's a rather complicated looking diagram, so let's simplify it to that. We now have the car modeled as a particle traveling around in a vertical circle. So now let's mark in some forces. First of all, the weight of the car. Now that weight is acting vertically downwards and is parallel to the vertical dotted line on the left. So that angle there must also be theta because they're just alternate angles. We can now resolve that vector mg into two components, the radial and the tangential directions. There's also going to be the normal reaction of the track on the car, r. So we resolve radially, and using force equals mass times acceleration, we can say the net force towards the center of the circle is r, plus mg cos theta. Using F equals ma, that's just ma, which is mv squared over r. We can now rearrange that equation to give us an equation for that normal reaction. But remember the picture. The car left the track when the normal reaction dropped to zero. Now we simply have an equation to solve with one unknown, theta. So, there's the equation we need to solve. The first thing we can do is divide out those m's. We can then move the g cos theta to the other side of the equal sign, divide through by g, and get that. Well, now it's easy. Because we know the radius of the loop, we know g, and we know the velocity of the car. So we simply stick in those numbers into the formula and find that cos theta equals 0.8503, 32 degrees from the vertical is the point at which the car leaves the track. Okay, let's look at this in general. Here is our vertical circular path, and here is our particle at some random point on the circular path, and it has velocity v, which, as we know from previous sessions, is r omega. We're going to define the position of that point by dropping in a radius, drawing in a second radius, which functions as a normal to the circular path at the point where the particle is, and we call that angle there theta. Notice that on this occasion, I'm measuring from a downwards vertical. As before, the equation for radial acceleration is simply r omega squared, or v squared over r. I'm also giving it to you in a third form, r theta dot squared. Theta dot is the same as omega. It's just the derivative of the angle function with respect to time. We need to think quite carefully about the derivatives of that angle function when we talk about tangential velocity. we now have tangential acceleration because the particle is not moving with a steady speed. Generally speaking, things going round in vertical circles get slower towards the top. If you look at that velocity v, we call it the speed around the edge of the circle, but it's really the tangential velocity. And because that tangential velocity is no longer constant, we can now differentiate it with respect to t and get that. R theta double dot. That is the conventional notation for tangential acceleration. We're not going to use it much, but you should be aware of it. Okay, what can we do with all this stuff? Generally, when we're talking about vertical circular motion, we're not talking about a powered vehicle. We're talking about some kind of particle which starts at either the very bottom or the very top of the circle and is given some kind of initial velocity u. This whole discussion is going to be conducted in terms of energy, gravitational potential energy and kinetic energy. So let's set our zero level for GPE there at the very bottom of the circle. The particle will start with kinetic energy of half mu squared. Using conservation of energy, we can see that once it gets up to that second point there where it has velocity v, a half mu squared is now going to be a half mv squared plus the gain in potential energy, where h is just that distance there. But we've got another way of working out h. You see, that length there is just a radius. So we can use a bit of trigonometry and get that length there as r cos theta. But of course, that entire vertical dotted line is also r. Therefore, h is simply r minus r cos theta. So now we've got a slightly more useful form of that equation because it uses that theta value, which is the thing we use to define the position of the point on the circle. Okay, let's rearrange that. First thing we can do is take out a common factor of r from the bracket on the right. Then, as we did with that specific example of the car and the track, we can divide through by m and then multiply everything through by 2 to get that. It's probably more useful to have an equation for v squared, because in general, we know what velocity we gave the particle at the start, so that is a more useful form of the equation. We can now calculate the speed of the particle at any point using this formula, provided we're measuring angles from a vertical downward radius. Okay, what else can we work out? We've got one handy new formula. What about an equation for the tension in that piece of string connecting the particle to the center of the circle? Or, in an equivalent setting, the normal reaction of the track on that car looping the loop. First thing we need to do is mark in some forces. We'll start by putting in the weight of the particle, that's mg acting vertically downwards, and we need to resolve that tangentially and radially. If we chase the angles around, it doesn't take long to see that that angle down there must be theta, so we can mark in the two components of that weight as mg sine theta and mg cos theta. Okay, let's resolve in the radial direction to see what's happening to the tension in that piece of string. Using F equals ma, we can write that F net is T minus mg cos theta, because of course mg cos theta is acting in the opposite direction to T, and the net effect of that force will be ma, or mv squared over r. We can rearrange that to get the tension equals mv squared over r plus mg cos theta. And we can now substitute v squared, which we have up there, v squared equals u squared minus 2gr, into this equation here to get that. We can rearrange things again a bit. We can make that mu squared over r and then divide the rest of it through by r. Then I guess we can expand those brackets, tidy up, and get tension equals that. It's not pretty, but it does in principle mean that we can now work out the tension in the rod or string at any point around that circle. So now let's see if we can apply all this to some actual example. We've got a particle of mass 50 grams attached to the end of a piece of string 75 centimeters long. It's hanging vertically and given some unknown impulse I, which has the effect of sending the particle whizzing round on a circular path until it reaches some particular given angle, at which point the string goes slack. We need to work out what that impulse was. You can either try it yourself and then watch this afterwards, or you can go through it with me now. So, if you want to do it independently, stop the video now. I'm going to start by drawing a diagram. Here's our particle. It's given some impulse corresponding to an initial velocity of u and sets off on this circular path. It ends up reaching some point up here such that the normal from that point on the path to the center makes an angle of theta with the vertical, and that angle has a tangent of 3/4. That means we can draw a little triangle like this and say if that angle at the bottom of that triangle is theta, those two sides there are in the ratio 3:4. Well, if you remember your Pythagoras, that means the hypotenuse must be 5, and we can write down sine theta and cos theta. You can't make any headway with this question unless you spot that. Once you've done that, you can start modelling the problem algebraically. We have our tension in the string T. We have our weight acting vertically downwards, which we resolve tangentially and radially. You need to chase the angles around that shape. That's a theta in there. So we can fill in mg sine theta and mg cos theta on that diagram. And we know that the tension in that piece of string plus mg cos theta give a net force delivering an acceleration of mv squared over r. We can rearrange that equation to get this. We'll call that equation 1. T equals mv squared over r minus mg cos theta. If you need to pause it now just to check where that equation comes from, you may do so. This all goes horribly wrong when the tension in the string falls to 0. That's the equation we've got to solve. So we now use energy considerations. The kinetic energy it has now is a half mv squared, which is equal to a half mu squared minus the gravitational potential energy it's gained. And h, the height it's gained, is that there. Now, as we did before, we can split that height h into two components, r cos theta and r. So that equation there can be rewritten in that form. We can rearrange that equation to get mv squared over r equals that thing on the right. And then we can replace this mv squared over r with that to get that. That's pretty messy, but as before, we can cancel out all our m's, then rearrange to get that. So u squared comes out as 32.34. You simply square root it, multiply it by the mass of the particle, 0.05 kilograms, and get that. The impulse is about 0.28 newton seconds. So to recap, here's what you should now know about vertical circular motion. First, the equation for radial acceleration is unchanged. It's r omega squared, or v squared over r. And you should also be aware of this other form, r theta dot squared, theta dot being the same as omega squared, but written as the derivative of the angle function. When you have variable angular speed, you can work out the tangential acceleration using the formula r theta double dot, or if you prefer, r d omega by dt. When you're dealing with a particle on the end of a piece of string, or a particle given an impulse to send it around a loop, when it has initial horizontal velocity u and position theta relative to a downward vertical radius, you can calculate the velocity at any point around the circle using that formula. Given additional information about the mass m of the particle, you can work out the tension in that string if it is a particle in a string, or the normal reaction of the track on the vehicle. You simply use the weight of the particle, and that formula there gives you the tension in the string. It's not that you need to remember these formulae, it's that you need to understand the process by which they were derived so that you can develop your own solutions to the problems you see. And that's it for this session on circular motion.